Hey guys, I hope you all are doing good. In this lecture, we will try to understand the strong induction, right? In the last lecture, we covered weak induction with some questions, and this one, we will cover what is strong induction in detail, right? Just like I said in the previous video, these two proofs are kind of the most difficult ones, and they need a lot of practice to have a strong hold in both of them, right? Okay. So before I start with the strong induction, I just want to give you guys an idea of what is weak induction, right? If you remember in the weak induction, we were trying to prove something for an entire set, right? Let's say maybe it is something for the entire set of integers, or maybe it was for the entire set of, let's say, natural numbers, right? And in order to do that, we kind of created a domino effect. The domino effect was we kind of went like if P1 is true, if P1, then P2, if P2, then P3, and this kind of went on, right, until the very end. So if you remember, let's say P1, let's say 1 is the first element, right? And if we prove the proposition or the predicate for the first element, and then what we did is we assumed the assumption that P of k is true, and using that assumption, we try to find out if Pk plus 1 is true, right? So think about it, right? If I prove Pk implies P k plus 1. This creates a domino effect because pk plus 1 will then imply pk plus 2, which will further imply pk plus 3, right? So I hope you understand how this works, right? Kind of a domino effect where I'm using one previous assumption to prove the next one. I'm, I'm assuming pk is true, right? Where k could be some value, let's say it could be any value, right? And using that pk, I'm trying to prove whether the next one, which is pk plus 1, is true or not. And if I prove this, then I've created this domino effect, proving that predicate for the entire statement, right? Okay, so I hope you have a good understanding of what is weak induction, right? Once again, try to solve as many questions as you can on weak induction, because I think that's exactly how you have a good understanding about this entire set. Okay, now let's try to understand what is strong induction. It is a variant of induction where the inductive step assumes all the previous cases and not just k. So what sometimes happens is that for a lot of proofs, just knowing or just making the assumption that pk is true is not enough, right? It's kind of like we are missing some of the resources that we need in order to prove p of k plus 1, right? So the basic point is that for a lot of questions, you might just need us make the assumption p of k, some value k is true, and using only the single assumption, which is the previous step, you will be able to prove pk plus 1 is true, right? This will create the domino effect. But for a lot of cases, what the point is that just having this assumption, just having one previous step assumption is not enough, right? So in that case, in the strong induction, what we assume is we assume everything until the pk is true. So from the starting element to the value pk, we assume that all these are true, and using this entire assumption, we try to prove pk plus 1, right? So basically, pk plus 1, what usually happens is that this pk plus 1 might depend on a few previous values for its answer, right? So if you remember Fibonacci sequence, then you might be able to understand what I'm trying to say, right? It basically depends on two previous values, and this is kind of like that this pk plus 1 depends on multiple previous values before it, right? Okay, so just a quick summary of what is the difference. In weak induction, we just assumed pk, and using that assumption, we tried to prove pk plus 1, right, which is the next assumption. But in the strong induction, we assume all the previous cases before the value k, including k, and that using that assumption, we try to prove pk plus 1, right? If you're not able to understand it, that's totally fine. We are going to understand a question in detail of how this works, right? Okay, so now let's try to understand when do we use it. When pk plus 1 depends on multiple previous terms, right? So this is very important to understand. So just like I said, right, it could be that this pk plus 1 value, in order to prove it, we need multiple previous assumptions, right? So in that case, we will use a strong induction, right? Just like I said, the more questions you solve, you will have an idea of whether pk plus 1 depends on multiple assumptions or just a single one, right? And second one is when weak induction fails. So if you feel like your weak induction failed, then you should try with the strong induction, right? What usually I do is, I would, if I see a proof and I'm supposed to solve it, then I would start with the weak induction, try to figure out whether I can find the proof with the weak induction. If not, then I'll use the strong induction to prove P of k plus 1, right? So that's the basic general way of solving these type of questions. Okay. Now, the structure of strong induction is very similar to that of weak induction. The first one, so for example, let's say in order to prove for all n, Pn is true, right? P is just a predicate. I hope you understand what that means, right? It could be an equation or it could be some statement that we are trying to prove, right? Base case, we verify P of n naught. P naught, n naught basically means the first element, right? So I'm just going to write this down. Of set, right? So base cases, we prove that this is true for the first step, right? But if you remember, in the weak induction, it was just for the first single element. But in this case, we try to verify it for some certain number of elements until some m, right? Now, what is this number m? So this number m basically comes from the fact or the understanding of how many previous assumptions we might need in our proof, right? It might sound weird or it might be confusing, but when we look at the questions, it might become a lot more clear of how do we figure out this number m, right? But for now, let's try to understand that this is basically a number that until which we are giving the values or giving the proofs for those values, right? So maybe, let's say I have natural numbers, then I'm trying to maybe prove in the first step for 0 to 5. So P1, P2, P3, P4, P5, because maybe in my question that is going to be helpful, right? Okay, so the difference between the base case of weak and strong induction is, in the weak induction, I was just trying to prove the first case, which is the P of 1 or maybe P of 0. In the strong induction, we prove for a certain previous steps, right? And we usually have to solve using the equations. Second one is, assume Pi holds for all I less than equal to k. So just like I said, in the weak induction, I was just assuming that Pk is true, right? That was my only assumption. But in this case, I'm assuming that the predicate is true for all the values until and including the value k, right? So Pi, I is less than equal to k. So a very simple example would be, let's say k is 5, then my assumption would be that P1, comma P2, comma P3, P4, P5 are all true. This is what I would assume in order to prove that P of 6 is true. So just a very simple example, right? In order to prove P of 6, I'm using all the previous assumptions until P of 5, right? Why is that? Because it might be that I need all the previous values in order to prove the P of 6. If you remember in the weak induction, I just needed P of 5, which is the previous, in order to prove P of 6, right? So this is the difference between weak induction and the strong induction. So assume Pi holds for all I less than equal to k. So for example, if k is 5, then we assume that P1 until P5 is true, and in order to prove P6 is true, right? And the inductive step show that this implies Pk plus 1. So in the inductive step, we are going to use all these assumptions, right, until the value k, in order to prove P of k plus 1. So the difference between weak and strong induction, again, we were just assuming P of k in the weak induction, right? And in this one, we are assuming all the previous values until Pk in order to prove P of k plus 1, right? Okay. Next one is just the final conclusion. Once we have achieved this point, we write the final conclusion, that is by strong induction, Pn holds, right? So I hope you are able to understand the difference between weak and strong induction. Just like I said, try to solve as many questions as you can on weak induction, because I think that would be helpful in understanding strong induction in detail. So now let's take a look at an example of a question with strong induction. So let's try to understand one of the examples of strong induction, right? The example says, proof f of n, which is basically a function, is less than the value 2 to the power of n, right? For all the values n greater than equal to 1. So I'm basically supposed to prove that whatever function value gives, it is less than 2 to the power of this n value, right? Okay, so we have already been given some equation for it, right? We are given f of 1, which is when we put the value 1 into the function, it gives 1, and 2 also results in a 1, right? And we have f of n is equal to n f of n minus 1 plus f of n minus 2, right? Okay, one important thing to understand is this is actually the Fibonacci sequence. So if you're a computer science student, then if you haven't covered it yet, you will probably cover it throughout your semesters, right? But this is actually the Fibonacci sequence, right? Yeah. So let's try to understand one thing, right? Maybe the first thing you can do is you can try to solve this question using the weak induction, right? But the problem is you will not be able to do it. Maybe you can give it a shot. So we are going to solve it using the strong induction instead. But I want to explain why exactly we cannot use weak induction in this case, right? So if you look at this equation, right? This equation has two different parts to it, right? If you see, this f of n value depends on not only the previous value of the function, but also on one another previous value, right? So it depends on two previous steps for the next step, right? Now, if you remember in the weak induction, what I assumed is I assumed that P of k is true, right, for some value k. And using that assumption, I was trying to prove P of k plus 1. So I was just using one previous step in order to prove the next step, right? So P of k, and I want to prove P of k plus 1 implies P of k plus 1. But in this case, if you look at this equation, right, that's not going to be enough, right? Because the problem is this f of n not only depends on one previous value, but it depends on two previous values in this case, right? And that is exactly why this is not going to be enough in this case, right? So this is just to give you a general idea of how you can figure out whether you're supposed to use strong induction or you should go ahead with weak induction, right? Okay, so now the steps are pretty much same for both the weak and the strong induction, right? With just one, with just a few small changes. So let's first take a look at the base case. So in the base case, now the very first thing is I see that this value depends on two previous values, right? So what I'm going to do is in the base case, instead of just having one value proven, right, I'm going to prove this f of n for two different values. And what are those values? They're already given to me in this function, right? So why am I using two different values in the base case? It's because this function depends on previous two values, right? So let's take a look at this, right? So we are supposed to prove f of n is less than equal to 2n, 2 to the power of n. Let's look at f of 1, right? Is it less than 2 to the power of 1? This is actually true, right? So 1 is one thing that has been proven. Let's take a look at f of 2, right? F of 2 is also 1. Is this less than 2 to the power of 2, right? So 1 is less than 4, and this is true again, right? So the base case is proven. I have solved that f of 1 and f of 2 is less than 2 to the power of 1 and less than 2 to the power of 2, right? So it is basically true for the first two values of this function. Okay, now let's take a look at the inductive hypothesis. Okay, so I'm going to assume f of I is less than 2 to the power of I for all values I less than equal to k. Okay, let's try to understand this step, right? If you remember, in the weak induction, I was just assuming f of k, and using that assumption, I was supposed to prove f of k plus 1, right? But if you look at this example, I'm saying for some value f of I, or for some value I, f of I is less than 2 to the power of I for all the values I which are less than equal to k. I hope you understand this symbol, which is the for all symbol, right? So I'm basically saying for all the values which are previous than k, right, which are maybe less than k. So let's say if k is the value 5, right, then 1, 2, 3, 4 until the value 5, the function is going to be true, right? So f of I is less than 2 to the power of I for all I less than equal to k. This is the inductive hypothesis in the strong induction, right? We assume that all the previous steps are true instead of just f of k is true or p of k is true, right? Okay. Now let's move on to the next step, which is the inductive step, right? Now, this is the step where you will understand exactly why we need this step, right? So let's look at f of k plus 1, right? Now, let's first try to understand what I'm supposed to prove, right? I'm supposed to prove f of k plus 1 is less than 2 to the power of k plus 1. So, to prove, this is also very important to understand that you know exactly what you are trying to solve, right? What equation you are trying to reach. So, in this case, we are trying to reach f of k plus 1 is less than 2 to the power of k plus 1, right? So, let's take a look at f of k plus 1. Right? What I can do is, if I know f of k plus 1, right, f of n is equal to f of n minus 1 plus f of n minus 2. So if I write it down, I get this is equal to f of k plus f of k minus 1, right? I hope you understand this part. Now, remember one thing. Now, according to our assumption, right, this is where the assumption helps us. I made the assumption that for all the values I which are less than equal to k, this assumption is true, that I'm assuming that this is true for all the values less than equal to k, right? So in this case, this f of k is less than equal to k, right? And k minus 1 is also less than equal to k. So maybe I can replace this f of k with this 2 to the power of k, which gives me 2 to the power of k plus this gives me this equation that this is less than 2 to the power of k plus 2 to the power of k minus 1. Remember what's the equation we are trying to reach? We are trying to reach that this is less than 2 to the power of k plus 1, right? Okay. So I reached down this equation and I need to somehow convert it to 2 to the power of k plus 1. Now, I need to tell you about a basic concept and I hope it will help you understand how this works, right? Okay. So if I tell you 1 is less than 2 plus 3, you would agree to it, right? But what if I tell you maybe I can change this 2 to 3 again? This would still be less than 3. So if I keep increasing this value, this one value on the left hand side would still be less than it, right? As long as I keep increasing the values, this equation will be true, right? So let's take a look at this equation. What if I replace 2 to the power of k minus 1 with 2 to the power of k, right? So what I'm trying to say is, if f of k plus 1 is equal to, sorry, is less than 2 to the power of k plus 2 to the power of k minus 1, right? But since I'm trying to reach this equation, what I can do is, instead of 2 to the power of k minus 1, I can replace it with 2 to the power of k plus 2 to the power of k, right? Because think about it, right? This 2 to the power of k would be greater than 2 to the power of k, right? 2 to the power of k minus 1 is less than 2 to the power of k, right? Okay. So that is why I can replace this 2 to the power of k minus 1 value with this, and this equation would still be valid, right? Okay. How does this help? Now I can combine this equation. Since I know 2 to the power of k plus 2 to the power of k, this is actually, combining this, I get 2 to the power of k plus 1. And hence, I've solved. Hence, f of k plus 1 is less than 2 to the power of k plus 1. And this is exactly the point that we were trying to prove, right? Finally, the final step is that I need to write, hence, by strong induction, and the following statement, right? Which is basically the statement in the very beginning. So now, just to give you a quick summary of how we started and what we did in this question, right? We were supposed to prove that this function f of n is less than 2 to the power of n for all the values n greater than equal to 1, right? Now, we have already been given the function value for two of the values, which is 1 and 2, and we have been given the general equation, right, which is the Fibonacci sequence. So since it depends on previous two values and not just one previous value, I know that I'm not going to be able to use the weak induction and I have to go ahead with the strong induction, right? So in the base case, first I solve two different values because I know I'm going to depend on two different values. Second thing is, I assume f of I is less than 2 to the power of I for all the values less than equal to some value k, right? Now, the difference between weak induction and strong induction is that in the weak induction, it was just f of k assumption. And in this one, it is all the values I until the value k, right? Okay. In the inductive step, I'm trying to show f of k plus 1. I can write it as, according to the equation, right? F of k plus f of k minus 1, right? Solving for this, since I know that according to my assumption, I can replace these two with 2k plus 2k minus 1. And lastly, what I did is I just replaced this 2k minus 1 with the 2k, right? Because this is actually less than it. And this equation would still be valid, right? So that is exactly how we solve this question. Now, I'll be giving a bunch of practice questions for you guys to solve. And if you guys have any feedback for me, or if you have any doubts, then I can solve these questions for you in another video, right? So I've given two questions on the board. The first one says, prove that any postage which is greater than equal to the $8 can be formed using $3 and $5 bills, right? So let me first explain what this question is trying to say. So it basically says that for any value of dollars which is greater than equal to 8, we can form them using a combination of $3 or $5 bills, right? So for an example, $8 is actually equal to one $3 bill plus one $5 bill, right? $9 is equal to 3 into $3 bills, right? $10 is equal to two $5 bills, right? $11 is equal to three. I'm sorry. Um, so two $3 bills plus one $5 bill, right? Which is 6 plus 5, which is equal to 11. So if you take a look at it and if you try to solve for a few, you can figure out that for all the values which are greater than equal to 8, they can be formed using a combination of 3 or $5 bills, right? One quick thing to understand is it doesn't have to be that the value of the bill you use has to be greater than equal to 1. It could be that uh, the three bills are maybe 0, or maybe you're not using the $5 bills at all, right? Okay. So, and I just want to give you a hint of what you're supposed to do, right? You probably understand that you're supposed to do this with a strong induction, right? But how do you do it? That's the important part. Remember, you're supposed to prove P of K plus 1, right? So this is what you're supposed to prove, right? Maybe what you can do is you can go back a few steps using one of these dollar bits, right? That's the actual hint I can give you guys. But maybe in the basis step, you should solve for three different values. And the reason I'm saying is because there's a value 3 over here. And then you should try to figure out P of K plus 1 by taking a few steps back, right? Yeah, that's as much hint I can give for this question. But if you're not able to solve this question, I'll cover it in detail in one of the lectures, right? Okay. So the second question is this one. The second question is very similar to the Fibonacci sequence question that we solved. So I think this question shouldn't be a big trouble. So that's it for this lecture. Now I'll see you guys in the next video.